Hello everyone. Today I want to introduce to you the concept of parametric equations. That is, how to graph them, convert them into function form, and a few cool applications.
So we know how to plot point in the form x, comma y. So for example, we can plot the point 2, comma 5. And we do that by saying, okay, it's 2 in the x direction, so 1, 2, and 5 in the y direction, so 1, 2, 3, 4, 5, and that's right here. And we also know how to plot a function, for example, y equals to x. And how we plot that is we make a table for x and y, and then we choose some values for x. So -5, -3, -2, 0, 2, 3, 5. And then from there, we find the corresponding values of y. So that's 5, 3, 2, 0, 2, 3, 5. And don't forget our negatives on the negatives, all right? And then we plot all those points accordingly. So 0, 0, -2, -2, -3, -3, 2, 2, 3, 3, 5, 5. That's right here. All right, and we see that makes uh, a straight line passing through the origin, right? And parametrics are not more complicated than that, actually. So what is a parametric first? Well, a parametric is written in terms, is written as x and a y in terms of another variable. Most commonly used is t. This is because most of the time when we're talking about parametrics, we like to talk about how far something is in the x distance, how far something is in the y distance, and then we use t as
The time it takes for it to be in that location.
we just refer to graphing coordinate points in representation x, comma y. And parametrics work in the same way as coordinate points do. And the only difference is how you look at x and y. Instead of having x and y be just a value each, they're rather a set of values. And most of the time, they're a function. And we know that functions are a continuous and a infinite set of,
Values that are defined by another variable.
and I said before that that variable is t. So let's look at an example. So first I'm going to represent this parametric in this form, in the coordinate form. So as 2t, comma, 5. Okay, this is the same thing as saying that x is equal to 2t and y is equal to 5, with the understanding that this together makes our equation. It's not that they're two separate equations, but together they make our parametric equation. Okay, so how do we graph this on this grid? Well, we make a table for t, x, and for y. Okay, we choose points or numbers or values for t, and since x and y depend on t, we find x and y from those values of t. So let's begin. Let's start with -2. Let's do -1, 0, 1, and 2 for t. Then x, in this case, is going to be 2 times -2, which is -4. And when t is equal to -1, then x equals -2. When t equals 0, x equals 0. When t equals 1, x equals 2. And when t equals 2, x equals 4, right? And I said here that y equals 5, right? These here are the same thing. So it's going to be 5 no matter what t is. And what do we get if we were to plot these points? When we plot these points, remember that we're plotting x comma y, not t comma x or t comma y. Sometimes you might get mixed up, but please make sure not to mix these up. We plot x comma y because in the Cartesian coordinate system, we are not, there's no space for a t. We are plotting x and y. So first we go -4, 5. What? -4 is right here and 5 is up here, right? -2, 5. That's right here. 0, 5, 2, comma 5, and 4, comma 5. And that appears to make for us a nice horizontal line. Okay? And if we were to express this line in terms of a function, first of all, is this a function? Yes, it is. Why? Because it passes the vertical line test, right? So this function, we would call it y is equal to 5. That's how we represent our horizontal line. So then you may ask, why then? What's the purpose of this parametric? Why then would I even have this part right here? X equals 2t. This y equals 5 pretty much takes care of this line for me. So why did I even input that at all? And the answer to that question is because parametrics sometimes gives us more information than we need. And that's a good thing actually, because sometimes life gives us more information than we need. And when we graph parametrics, we're only looking at the path that it might take over time. But parametric gives us more information than the graphs does by itself. Parametrics tells us how long, like if we say that t is equal to a time, and we say x is equal to an x distance, y is equal to a y distance, then parametrics also tell us when you could get to a possible location. For example, let's say you are a car. That's this red point right here, okay? And I said, and let's say that you're traveling along the x distance, right, at 2 miles an hour. That's what this 2t represents if t is time given hours. And your y distance is always 5 miles, okay? Then this tells us that at time t equals 0, you are right on the y-axis. And at time t equals 1, you are 2 spaces eastward of the y-axis. However, let's say you're traveling slower. So let's say instead of traveling at 2 miles an hour, you're now traveling at 1 mile an hour, which means that in 1 hour, instead of being 2 miles away, you're only 1 mile away. Although you're still going along the same path, now that your speed has changed, your location has changed. And the graph doesn't show us that, but parametrics do, because it has a time value here. So I hope that clears things up and makes a lot of sense. This example is x is equal to t squared over 2 and y is equal to t plus 1. Also to be written as this. Again, this represents the same thing that these two equations do. Okay, so let's see what that looks like and draw a table. Let's choose some values for t. So my first value I'm going to choose is going to be -4. My second value is going to be -2. Then I'm going to do 0, 2, and then 4. And let's see what we get from these points. So when x is equal to, when t is equal to -4, x is equal to -4 squared over 2. What is -4 squared? Well, that's -4 times -4, which gives us a positive 16. 16 divided by 2 gives us 8. So when t is equal to -4, x is equal to 8. And when t is equal to -4, y is equal to -4 plus 1, which is -3. Okay, let's go to the next one. When t is -2, x
Is equal to 2.
and y is 1 more than t, so that's -2 plus 1 or -1. When t is 0, x is 0 squared over 2, which is 0, and y is 1 more than 0, which is 1. When t is 2, x is going to be 2 squared over 2, which is 4 divided by 2, or 2, and y is equal to 3, right? And lastly, we have 8 once again. In this case, for y, we have 5. So we now plot these points. Our first point is 8, comma -3. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. That's right there. Our second point is 2, 1, 2, -1. That's right there. Our next point is 0, comma 1. That is right there. Our fourth point is 2, comma 3. Right there. And our last point is 8, comma 5. Right there. And do you recognize this shape? And if you do, you might say, yes, it's a parabola, except it's sideways, which is, I might not have seen that before. It's a sideways parabola. That's really interesting. And that shows the inherent power of parametrics. We can also show and create relations that are not necessarily functions. In this case, y is not a function of x because it does not pass the vertical line test, right? But y is related to x in some way, and if we were to try to uh, solve this as a function, we would actually get um, a square root curve. But we don't have to do that right now, right? But do you see how this could be a square root curve, or at least half of it, how it is a square root curve? See, we know square root curves look like this. And that's exactly what this is here. And it appears to be so. This is the graph here, and you see I can move the point around it freely. That's changing the values of t. But that is the curve that this point, or the path that this point will follow, and it can follow continuously. Last parametric I want to show you is a really interesting one. This one here, x is equal to the absolute value of t. And the second one, y is equal to the absolute value of t plus 4. So we go ahead and do a table. Okay, so let's plot our, let's find out our x and y coordinates. So when t is -8, x is the absolute value of -8, that is equal to 8, right? And since we know that the absolute value of a negative or positive number is always going to be the positive value of that number, so we can go ahead and fill out the table for x's. For the y's, we need to be very careful because this says the absolute value of t plus 4, not the absolute value of t plus 4. And what's the difference? The difference is you need to do the t plus 4 first. So in this case, we have negative 8 plus 4 is negative 4, and the absolute value of that is 4. When t is negative 6, we have negative 6 plus 4, which is negative 2. The absolute value of that is 2. And we go on. Negative 4 plus 4 is 0. The absolute value of that is 0, right? Then we have negative 2 plus 4, which is 2. The absolute value of that is 2. The absolute value of 0 plus 4 is 4. The absolute value of 2 plus 4 is 6. And the absolute value of 4 plus 4 is 8. And let's plot all of these points to really get a good picture of what we are looking at. The first point is 8, comma 4. That's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. That's right here. Then you have 6, comma 2. 1, 2, 3, 4, 5, 6. 1, 2. It's right here. 4, 0. 1, 2, 3, 4, comma 0. That's right here. And I have 2, comma 2. 1, 2, 1, 2. And then 0, comma 4. And then 2, comma 6. 1, 2, 3, 4, 5, 6. And then 4, comma 8. And what do we see? Let's graph one more point to really finish off. Let's say we use 6, okay? Then x is equal to 6 and y is equal to 10. So that's right here. You see that's this over here. So it appears that we have what looks like uh, a beam that bounces off the two axes and then goes back, almost making a square, but it doesn't close a square, but it's almost like a square, and it's really interesting to look at, right? It looks like a laser beam, pew, just like that. And let's verify, make sure that that is exactly what we should be seeing. And as you can see here, that is exactly what we should be seeing. And it really does look like a beam or a ball is just suddenly bounced off the two axes and it's just going right back out into space. There's one more little thing that I believe it could be interesting to really show you.
Physics uses parametrics a lot for projectile motion and trajectories.
Just means the motion of an object when it's thrown or when it's launched, like a rocket ship or a football that is thrown. So let's say, anyway, we have one of these footballs, okay? And let's say we throw it from a height of 1 meters. So let's say the quarterback here is 1 meter tall. And let's say that he throws it with a speed of 10 meters per second, okay? That's the initial speed. And you see that if we decrease the speed, the football, you know, doesn't travel as far. And he throws it at an angle of pi over 4, which means 45 degrees. If you don't know radians, that means 45 degree angle. How far away from the football player will the ball eventually land. And we can solve these problems using parametrics. This here is the equation or the equations for the path of the football, and it's the same for the path of any projectile. And you don't have to recognize or remember this equation, but it's the purpose of this is just for me to introduce to you if you've not seen it before, and also to just show you how parametrics are applied. So what would be the answer to the problem I just asked? How far would the football land? So I know land when the y distance or the height is 0. So let's see where that is. So let me increase the bounds of the t. Okay. So what I just did there is I said, okay, the starting point, I started at 0 seconds. So at 0 seconds, right? It's right there. I don't know if you can see that point, but it's right there. At 1 second, the ball is right here. At 2 seconds, the ball has already hit the ground, right? So it appears that it hit the ground at around 11 point, I would say point 1, 11.15, 11.12, 11.12 meters away from the football player. That's really interesting. At what time did it get there? Let's see if we can get this number really close. So 1.5. At 1.5 seconds, it's almost there. So let's see 1.6, 1.55, 1.58. And it's like around 1.57 seconds, the ball has hit the ground. Around that, right? And with this, you can also find out what was the maximum height that the ball traveled. It seems that at 5 meters away from the player, the ball reached its maximum height of around 3.5 or 3.6, 3.5, 3.6 meters, right? That's pretty interesting. We couldn't get all this information from just a function or just a parabola. We know that this is a parabola and this could be represented in function form, but we might not have been able to get all this information that we're getting just from that alone. Because with parametrics comes not only our height, that's our y distance, our range, our x distance, but also t, our time. And that's the time it takes where the ball is at that specific time. So that just goes to show how useful parametric equations are. So thank you very much for tuning in to today's lesson on parametrics. Don't forget to like and subscribe and get updated whenever we have a new video out. Thank you.